So welcome to our sixth class in data analytics, where we explore interactive visualization, probabilistic modeling, and machine learning using Mathematica as your learning platform. And this platform can then go on and serve as your sort of prototyping tools whenever you need to work out some idea. As I probably mentioned to you before, in my own project, I use Mathematica to work out the mathematics and the model that I want to try, and until I'm happy. Then, once I'm happy, then I can turn to my team kind of implementation or, coder to translate that into more ubiquitous Python library to do that. Anyway. So the first week gives you the concept of data analytics. Why are we doing this course and the objective of that learning? And as I alluded to from the very beginning, it's supposed to give you the conceptual understanding of how things work. You will not be necessarily see yourself as the DevOps kind of guy, right? Where you develop the software from the ground up, or even using basic open source library to build up application, but certainly to use it in your application. So some of you may go on to apply digital intelligence, in which case you might go on to do more coding, presumably using more general purpose language like Python and so forth. But a lot of you could then go on to focus your BSI program, your BSI undergraduate program, along the line of sustainability and smart city studies, or sustainability, healthcare, and health and well-being track. In which case you might want to play with some data set, and it would suffice for you to get some preliminary understanding of the relationship. So you use, interactive visualization, but then you start to want to do more understanding of the statistical property or distribution of your data set. And eventually you might want to apply machine learning algorithm so you can gain more insights into the data set. Okay. Now, as is clear in the subtitle of the textbook I used for this class, textbook I wrote for this class, there are three kind of groups, right, of knowledge. Interactive visualization, which we concluded last Tuesday. Thank you. Okay, so interactive visualization, what's the upshot of that? Again, number one, the upshot is sometimes just by doing the right visualization, you get the insight that is already actionable. You can act on it. You can see where the bottleneck is, where the pain point is. You can know where the efficiency gap is, blah, blah, blah. You can see where your client sector is and where you should focus on your marketing effort or whatever, okay? So first thing is interactive visualization immediately gives you the insights into your problem, and you can act on it right away. The interactive part helps because, at first try you plot, X1 versus X7, and it doesn't give you any insight. Maybe you can try different thing, different transformation on X1, or maybe X1 in combination of X2, or any kind of slice and dice, mix and match. And that's where interactivity comes in, right? So you can sort of like play around with that. So the interactive tool is something that can be useful like right away. Secondly, it is actually a tool for data scientists proper to get a basic understanding of what the data they're working with. So this will be something that I emphasize a bit more for your class, meaning that even if you're working as a data scientist, once you get the new data set, you want to yourself understand what the data looks like. Okay, so the insight is not for the end user. The insight is for the data scientist himself or herself to come to understanding of what data am I playing with. Okay. So this is a sort of like a tool to guide the model building. Okay, so that's a second value of a proposition of having quick and easy and robust interactive visualization tool. And the third is, once you've done the data analytics, you know, whether it's traditional econometric model or regression-based analysis or advanced machine learning or any kind of graph theoretic representation or whatever, at the end of the day, you have to present the result. And once again, the result can be of this quantitative analysis can be quite complex, right? And you need to ground it in data. You need to ground it in numerical finding, but you also want to make it intuitive to the end user or to your client. In which case, interactive visualization is then used to visualize the result of your analysis. Okay, so it's used from the beginning, the middle, to end, if you will. Okay, so the beginning, well, maybe not beginning, middle to end, but certainly three-part, right? You can use it right away, boom, get the insight. You can use it to inform the model builder, or you can use it, the model builder can use it to communicate the result of the finding. Okay. Now, so that's interactive visualization. That's basically what we spent the last, I think, two sessions, right, on. And now we go to this session, which is probabilistic modeling. Now, this is more in line with your traditional probability and statistics subject. Okay. However, the emphasis will be quite different, and in particular, my coverage will probably highlight a lot of the reason why traditional assumption about probability and distribution may or may not hold. Okay, and that's to a large part, that's going to be paving the way for the last module, which is machine learning. Okay, so today it's let's start as if we're talking about traditional class in probability theory and statistical modeling. Okay, so chapter 1, we did that. Okay, chapter 2, that's the baseline. By the way, I hope you go through this exercise one by one by yourself. Just literally copy verbatim the mathematical command that's in your textbook, so you can get a feel of how it works. Okay. So interactive visualization, right? So this start with static visualization and then adding the interactive tool, usually manipulate. For midterm, basically, you'll be given that kind of interactive visualization class, right? So maybe I'll be giving you a link to a sample set of data, or maybe I would use some random generator to generate a data set and ask you to create a visualization. Okay, so we'll use all kind of the plotting, and in combination with all kind of options, right? And the options would then be controlled using the manipulate button. Okay, right. So today, and hopefully, I'll try to see if I can squeeze everything within today, this probabilistic modeling, because even though the subject is vast, the basic intuition behind it is fairly uniform. In other words, once you understand one distribution, you can also understand similar distribution or other distribution. Okay, it will be different flavor, it would look different, but it's a bit like cooking, you know the cooking principle. Then you don't have to spend 2 or 3 sessions learning so many dishes. Okay, right. I'm gonna follow, I guess, traditional progression in the subject, starting with what's called descriptive statistics. Now, this is kind of interesting. I want you to look back a little bit. You see, my book, right, has data analytics, visualization, and model, probabilistic model, and machine learning. And the first part, like I said, is about visualization. That's giving you an idea. Well, if you imagine, okay, if you imagine the world before computer graphic, okay, Before all that, when all basically we had was well, pen and paper, okay, and table of calculation. Okay, so people back then did a lot of massive amount of calculation by hand. Okay, so if okay, and they also use plots. Obviously, they use manual plots. But imagine that in the world of statistics, to visualize the data, okay, does not necessarily mean drawing a plot. Sometimes visualization means getting an idea of what your data looks like. So visualize in your head, basically visualize in your head. And if I ask you, for example, I use the word visualize, okay, but I say, I go to this country, right? Country where people are on average 1.5 meters tall. And on average, they weigh about 40 kilograms or something like that. Okay. Now, I'm not drawing any picture, but you can see that this is I'm giving you the visualization of it, right? Right. So in a way, statistical description is probably like an earliest form of visualization. Okay, it's not using visual language like a graph, like like plotting x versus y, and then arrows or whatever. It's not using that visual language. Yeah, it's using numerical summary. But that's what I mean by you're getting that visual picture in your head, right? Oh, in this country, people are small and short, or these people are very heavy. You can say Pacific Islander, they prefer people to be very heavy. Okay, so you can say, imagine you go to this island and people on average weighs about 150 kilograms, and that's an average. You say, oh, I can see, So you visualize that in your head. You picture that in your head. So when I say visualization, in that case, it's sort of like getting an idea of what your data looks like. Okay. So that's what descriptive statistic is, really the precursor of everything. Okay. So if you think of the world before all this data analytics and computer visualization and 3D plot and heat map and all kind of stuff, all you had to do was just, a bunch of numbers and maybe basic plotting. You can think of statistical summary, like what's the average? Okay. What's the minimum? What's the maximum? These are statistical average. That is the first thing you use to summarize the data, but not only summarize data, it actually helps you visualize the data. Okay. Now you will hear sometime I like to step back and say, what are we doing in data analytics, in all of machine learning and all this? Basically, you're just trying to get to know the population, right? As represented by some numbers. Okay. And that numbers, again, can be real number like the height, could be ordinal number like scoring, could be a nominal number like sex, male and female, right? So you can think of male and female as 1 and 0 on a nominal scale. So you kind of like trying to get the picture of the numbers. And I maintain that today, which is traditional probability and statistics, very traditional, going back 300 years. And next week, when you start, when we go to machine learning all the way up to 2024, state of the art in large language model, when you try to learn about data, it basically comes to two questions. Okay, where are they? That is, where are the data? Where are the points? Where are the x's? And the other one is, if there are two quantities, how are they related? Okay, so where are they? Where are the x's? Okay, and relationship, how is x related to y? Right? And these are the two fundamental questions. Now, I'll make my observation. Okay, it may not mean much to you right now, but this is what I'm going to say. In probability and statistics, traditional studies in probability statistics, you spend a majority of time studying where things are. So you spend a lot of time studying the distribution. And you spend maybe 20% of a class time learning about relationship between numbers. And that's when you will learn regression analysis. Okay, so if you look at traditional statistics, probability statistic textbook, okay, that may be like 500 pages, and maybe 80 pages would be devoted to regression, which is about how X and Y are related. Everything that comes before that is about the distribution of X. Where are things? When you go to machine learning, funny enough, the emphasis tend to be the opposite. Okay, if you take like a machine learning class, I would say maybe 60, 70% of that will be spent on what we will call supervised learning, which is a lot of it is about predicting Y given X. And a lot less on things like unsupervised learning, which is to say, I'm not trying to find out how Y relate to X. I just want to know where X's are, except X is multidimensional. Okay, so you know, bear that in mind. In the probability statistic world, where are things occupies the majority of the analysis, and how are quantity 1 and quantity 2 related? That's sort of like a smaller focus. Whereas in machine learning, it tends to be the opposite. It tends to be, if I know X, how can I predict Y? That tends to be the big focus of everybody. But where are the X's in high dimension? Where are the X's in this multi-dimension that I can't visualize? How can I see it in a smaller dimension? You know, how are the data organized? That tend to be secondary in focus. Okay, so that's right. Okay, so now what I'm gonna do is well, first of all, I'm going to define this thing. You can type along with me if you like. Don't have to type everything. Okay. But so as you will see, this is what kind of data structure is this with the funny bracket and arrow in between? It's an association, right? It's an association. Now, it's an association, and this is the name or the keys. This is the values. Okay. Now, what does any of this mean? What does any of? Well, I'm just making example. Okay, example. Okay, right. So what I did was I created like a demo data. Right, is equal to say 1. And I point to something like, you would see something like normal distribution. Okay, let's do that. Comma. And my second tool is something like, say, uniform distribution. Okay. And obviously in the example, as you see on page 95, I also give you example of student distribution, give you example of gamma distribution. And the first one, just ignore for a little bit, the Fibonacci one, okay? But basically, these are names, okay? These are names. So I told you about this declarative function, right? I want to be working with a normal distribution, okay? You remember that? I want to be working with a normal distribution. It's just a name, okay? So right now, I'm just naming, so when I call demo 1, okay, I don't have to write this long thing, okay? That's all it is, okay? Now, so these are normal, these are probability distribution. Okay. What has that got to do with what's that got to do with descriptive statistic? Not yet, not yet. I'm using this to generate. Okay, so forget about this. This is something that I use to generate some data to visualize. Okay, so that's what happened in the first page, right? Now, what I did was okay. Now we go to statistical moment. Okay, So this is where the proper lecture begins. Okay. Descriptive. Statistic. Okay. Descriptive statistic. What does statistic means? First, you have to think of statistic as numbers that summarizes number. Okay? Now say that in your head. Statistics are numbers that summarizes numbers. Okay. So, if I were to describe all the height of the people in this room, how many numbers do I need? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? If I want to summarize with just one number, what number would you make it? Would you take his height? No, right? Because when you summarize something, that doesn't mean you don't have access to the whole thing. It just means you can't write down the whole thing. Does that make sense? I want to write down everybody's height. Everybody's height, but I only have like such a tiny piece of paper. Or like I'm sending a telegram. Okay, and I have telegram back then is very expensive. So if I type in 10 numbers, cost me a lot of money. I want to summarize it in one number. What is the most information-rich number you can think of? An average would make sense, right? But I tell you what, not always. Let's say, okay, I come to the new town, you guys are my people, and you are my target. And I want to sell you shirts or something like that. Or I want to sell you something that's height related. It would make sense for me to say, okay, the average people in this room is 1.7 meters. Okay, more or less. Okay, so that makes sense. What if I have room for two numbers? Room for two numbers, not one number, two numbers. So statistical is number that somehow summarizes lots of number. Okay, so if I have, I'm going to erase this a lot, so don't worry about so if I have, I'm just going to write down your height as x1, x2, okay, and let's make it x100 so that it looks like it's going to take a lot of room. Okay, a very good, intuitive, and sensible way of representing hundreds number with one number would be to take an average. Okay, fine. So I'm going to call it x bar for average. Okay, so that's one number. Another number, I give you another number. So obviously the smartest thing is not to take the first one or the second one, right? So what's the second number you're going to do? What is another number? I have a slot for another room. What number would you give? Now, most of you have already done statistics. So most of you will probably say, if this is a mean, that's the first number I'm going to give. The second number is going to be S, standard deviation. Who would say that? Standard deviation. Okay, standard deviation. Why? Because this gives you a very good picture. People in this town are about 1.7 meters tall, and they're more or less within the bound of plus or minus. That's what you want to say. Okay, but it's not a strict bound. Okay, now let me just undo your learning a little bit. What if this is a little bit morbid? Let's say I'm not selling you shirts. I'm selling coffin. Okay? I'm going to call home and say, oh, make 100 coffin. Actually, what's the most important number then? Would be the maximum height, right? Because if I make a coffin that fits the tallest guy, it fits everybody. Okay? So even if you think the mean is the most important number, not necessarily the case. Now, keep that in mind. Most of the time, the right answer is the average. The maximum is not the most useful. But I'm going to, by the end of the class, you will see why maximum of a sample is also a useful number. Okay, but without being morbid, not just selling. But anyway, so now this X bar, mean and standard deviation. If you say standard deviation is 10 centimeters, can there be people who is taller than 170 plus 10? Yes. Yes, because by nature, this is a summary, okay? An average is not the maximum, and standard deviation is also a kind of average. It's the average deviation from that number, 1.7, okay? Fine. So what statisticians do is to say, okay, let's do this game. Let's do this game. Okay, so let's be a little bit more detailed. So what means sum, right? You know the notation, right? I going from 1 to 100 or the sample size, xi divided by n. Correct? Correct? Okay. Now, this kind of calculation where you take sum of the number, they will call it moment, statistical moment. I'll tell you why later, okay? It's a little bit like, well, it's take inspiration from physics, but anyway. So this measure you where you are. And I just told you, right, in all of statistics and even machine learning, you only ask two questions, how are X related to Y and where's X? So right there, it answers where is X. What about S? S just refine that question. S refine that question. Why? Because it's saying that once I know that, picture in your mind, people are about 1.7 meters tall. That's the first anchor point. Around that, people are either taller and shorter. In some population, that deviation is big. So yeah, 1.7, but you also very short, very tall. On average, it's 1.7. On the other hand, there's another population that's 1.7, but also everybody's almost the same height. By the way, which one is easier which one is an easier market to make a shirt for? It's the one with the less deviation, right? Okay. And yet it's answering the same thing. How big of a shirt? How big of a coffin? How tall of a bicycle, right? It's where they are. Where's X? Fine. Now, with standard deviation, you know how to calculate it? You calculate by taking the deviation from X bar, right? You take the deviation from X bar, except if you did this, by definition, what's going to happen? What's going to happen? By definition, this will be 0. Okay? Because if you take an average and you take the distance from average, some people will be taller than average, some people will be shorter than average. The distance from that, the average distance will be 0. So this has to be 0. So, and here's a funny thing. I'm going to write this in red. This is what you want. You want absolute value. Okay? Okay. This is called mean. Mean. Okay, the first one is mean. Mean is the average, right? Mean absolute deviation. Mean absolute deviation. This is actually the one that if you didn't have any class in probability statistics, this is how you would define deviation. Okay. However, we don't use it. Why? Why? Well, because before computers, you have to use things that are easy to compute with mathematics. And this is not a nice function in mathematics because this function looks like this. Okay? It's sharp. It's sharp. Now, who doesn't like sharp things? If you're a chef, you like sharp knife, but nobody else likes sharp things. Who else doesn't like sharp things? Calculus doesn't like sharp thing because when it's sharp thing, the slope from the left side and the slope from the right side is not the same. So there's discontinuity. So how can I get something like this where if you're shorter than average, you add to the deviation. If you're taller than average, you add to the deviation. Well, the trick around it is to say, well, I don't take an absolute value, but I take square. Okay. So this is called a sample variance. Okay. It's a variability around the mean square. But because the unit is all wrong now, right? Because it's to the second order, right? So if you talk about meter, this becomes meter square. It makes no sense. So let's do this and then take the square root of it. So it becomes the standard unit. So it's called standard deviation. That's a reason why it's called standard deviation. It's a deviation square. And then, you know, taking the square root so that it goes back to the same standard unit. Okay? Now, fair enough. Fair enough. Fair enough. Okay. Now, once you've done this, okay, statistician gets carried away. They say, what happened when I do this summation and instead of raised to the power 2, I raise to the power 3. I raise to the power 4. You know, forget about y, just for fun. Okay. Hey, I can take average of x. I can take average of x from the deviation square. Why not x deviation cube? Why not x deviation fourth? So this becomes what's called moments. That's why the general term for this becomes statistical moments. So you can see why that in the textbook, the first word is 1.1 statistical moments. Okay? Now, in practice, there are only 4 moments that you're going to worry about. First, second, third, and fourth. Okay? First, second, third, and fourth. I'll tell you why later. Okay? But so think of this kind of calculation. Okay? Now you don't care. So anytime you have a sum, okay, and then you have something by n or something, okay, and then you raise to the power 1, 2, 3, or 4, okay? So that's first, second, third, and fourth. If before you raise to that power, you subtract, it's called centralized. Okay, that's just terminology, okay? So first moment is the mean. Second moment is the variance. But the variance doesn't have a nice unit, so you usually take a square root of that, right? And usually by variance, you subtract. So this is why the definition is all there, right? The definition you can see is all there. And right. So how does this help? Again, think of a limit. You have a whole 100 numbers. You have room for one number, you put in the mean. You have room for another number, you put in standard deviation. If you can put in the third number, anybody want to guess? You put in the third moment. If you put in if you have four number, you put, okay, that's it. That's the end of story. Why does that make sense? Why does that make sense? Anybody? Because you have to have implicit communication that this particular population that you run into is typical. In other words, what do I mean by typical? When I say typical height, is people, if you take hundreds of people and you take an average of the height and it's 1.7 meters, you would expect to see a lot of people close to 1.7, right? Right? Now, unlearn that picture. Is it possible that I go to this population and it's a very freaky population? Every person is either boy or girl, and boys are exactly 1.8 meters tall, and girls is exactly 1.6 meters tall, and they're 50% of them. Just you know, just some really weird population. Okay, is that possible? Yes. Can I tell that apart from the mean? No, because the mean of this. Okay, so I'm going to present the first one. I do a little histogram. It's going to look fairly normal, right? A bit like that. Now the second distribution will have like this. Now they both have exactly same mean. All right, exactly same mean. In fact, I can adjust the width of this so that it matches not only the mean. So let's do this again. Let's say this is one histogram, and this is another histogram. Okay, and they have exact same mean, and just happen to be that I calculate the standard deviation is exactly the same. Okay, I can do that. Well, let's make it even more horrible. I can also do this. What? This is really freaky now. I can have another one which is like this. Okay. That population will also have the same exact mean and exact distribution, exact standard deviation. I can adjust the numbers, so it's exactly the same. However, if I compare the blue and the orange here, what would not be the same? Actually, when I take the third moment, it would not be the same, because it's going to punish the high value to the positive. It's not going to punish, it's going to add a lot. Okay, it's going to subtract very little, because when you take third power, the farther it is, the more influential, right? So this thing is going to make means a lot. So in other words, this thing and this thing, even though with respect to the mean, balances out perfectly, right? Balances out perfectly. When you take the cube power to the power 3, the one to the right is just going to pull the weights to the right. This is called right skew. Okay, so now I can also draw another picture like this. Right skew. So that's where the third moment comes in. Okay, and the fourth moment, well, if you think about it, the fourth moment is what distinguishes this bottom yellow from the top yellow, because the top yellow is very spread out. Okay, so it's very, very. Let me draw another picture. Okay, so this versus this. How do you tell them apart? First moment. First moment, tell them apart. Okay? So first moment, tell them apart. This versus this. Okay? What's going to tell them apart? Second moment. This versus this. Who's going to tell them apart? It's the third moment. And finally, this versus this. Who's going to tell them apart? Fourth moment. Okay? Now, what I've done here is to have two sides of the story. This is what you should have in your head. This is what you should have in your head. This is what you should have in your head. This is the picture in your head. This is the descriptive statistics. Okay? So descriptive statistics communicate basic picture. Again, I'm trying to tell you that all this thing came before computer, before this you can't send a fax. Think of the world where you can send a telegram, you cannot send a fax, right? So I do the market survey of 100 people and measure how tall 100 people are. Now I want to send that data home, right? If I have an email, I can just send the text file, the Excel file, right? Spreadsheet. I can only send one thing. Well, if I happen to have a fax machine, maybe I can do the histogram and send it, fax it. But I don't have a histogram. All I have is a telegram, okay? Which is one number. So the first number I'm going to send is 1.7. That means that everybody on average is around 1.7. Second number I'm going to send is something like 10 centimeters. Okay? And that tells the people at the listening end that most of the people are within plus or minus 10. Not everyone, but a majority of them. Okay? How big of a majority? We'll come to that. Okay? Third, I'll tell you the number that this skewness is negative. What does that mean? It means pulls a little bit to the left. So in other words, it's not quite symmetric. If you line people up around 1.7 meters, there's some taller, but there's some who are very short. So you have that kind of negative skewness. If I say that it's positively skewed, then it would be like, proportion of basketball player or something, someone very tall. Okay? So right away, within this first two page, okay, I just gave you the sort of like historical visualization 300 years ago. Okay, so visualization and communication and summarization tool 300 years ago before you have a fax machine. Okay, you can only tell people that. Okay, so imagine that somebody takes an average height of a bird in the Galapagos and measure the height and then send a telegram. Well, you can have a telegram, Okay, so that's what we mean by descriptive statistics. Okay, that's it. It just summarizes the data. Think of it as give you the summary that you can then reconstruct the histogram in your head. Okay, but this is still not data, right? Because histogram is actual data, can be very different. Okay, fine. So okay. Again, I'm going to spend a lot of time on where are data, where are the x's, where are the x's. So that's it. So that's called, so you can see the first moment, second moment, first moment. If I want to expand on it, okay, so that's looking 1, 2, 3, 4, right? But I'm going to go back to the first moment. The first moment is a good summary of where the middle are. Okay. However, is that the only one way? So this kind of thing is called moments, right? So, moment. But I'm just going to go back to the first moment. And I say, what does the first moment tell you? Well, it tells you where the data is, but it doesn't tell you where everybody is. In fact, for that funny population, 1.7 is never correct, right? Because half of them is 1.6, the other half is 1.8. Nobody is ever 1.7. So you're not really accurate, are you? It's like saying, I'm taking penalty shot. Half the time I shoot to the left, half the time I shoot to the right. On average, I'm the most accurate shooter in the world. Does that make sense? Right? Okay. So there are many ways. Now, let's be a little more clever. Let's say I really want to focus on the majority. There's some very short people, some very tall people, very abnormal. So I can exclude that. So maybe I take an average, but not the whole population, average of the 80% in the middle. Okay. So basically I have them line up from shortest to the tallest. And I say, the shortest 5% and the tallest 5% go out, go away. I'm going to take an average. Okay. Once I've done this, I thought, wait a minute, I can do something else. I can say, hey, line up from left to right. I drop off the bottom 30%, drop off the top 30%. I have the middle 40%. You know what? Every time I do this, I still have to calculate 40 number, right? So I get a little bit lazy. How about this? How about I drop off 45% on the left, 45% on the right. I only have 10% left in the middle. Okay. Then I get really lazy. I say, I'm just going to find a guy in the middle, take that guy. That's a decent number, right? Because after all, that's where the middle is in some sense. So all this become equally valid as a way of saying, where is the middle? Where are they? Where's the representative sample? The representative sample is everybody, take an average. Representative table is take the middle 50%, take average of that. Or the middle guy is take the middle guy and don't take any average, just take that one guy, right? And if you have 101 person, there's one guy in the middle. Okay, if you have 100 person, there are two guys in the middle. So you take two average, the average of the two numbers. Okay, so you're really lazy. You're really lazy because you don't like to do this calculation, right? So instead of adding 100 number and divide by 100, or adding 50 number and divide by 50, I just add two number, divide by 2. I'm so lazy. That's called the median. Okay, so you can see why measure the difference. This is like, again, this is way 300 years ago. These are sort of like shortcut way of communicating. Okay, and if you look back at, say, population consensus in history, they'll do this kind of thing. They'll do this kind of thing. They'll report this kind of thing. So the most important number you can take when you want to, where is the middle? You can do the mean, or you can do the median. Okay, you can do the median. Okay, and you can also do this. Imagine, okay, imagine. This is the population. If your population is like this, you would maybe make a shirt about this big. So that sort of like covers your market, right? Right? Now imagine this is your population. So that the mean is over here. This is the mean. But the population is 90% of the people are this big, and there's only 10 guys that's that tall. Wouldn't it be better if you just say which one is the most usual, right? Because you're trying to sell the most shirt. You really don't care, okay? So now, you don't care where the central in that average sense is. You care about where's most everybody. In which case, if your most everybody is 1.65, why would you make your shirt 1.7 tall? right? It's be too big for 99% of the people and too small for one guy or 10%, right? That's no good. So in this case, you look at the histogram and you find out what the peak is. We call that the mode. Okay. Now the mode is not as usually used. Okay. Mode is the most often. Okay. It's basically the peak concentration of height. Okay. So these three are the valid ones. Okay. However, there's a very good reason why in most probability statistics class, you don't really hear of median. You don't. Normally, you just hear the mean, you go on. In fact, most class, you never heard of the word mode. Okay? Those two don't really enter much in a high school statistics class. Okay? Some of you may have never, maybe seeing this for the first time. But mean, certainly you've seen it plenty of times, right? Well, there's good reason beyond the fact that it's intuitive. Okay? And it's the fact that it is also serving as a parameter for a special distribution called Gaussian distribution or normal distribution. Okay, so there's technical reason why you only learn about this one thing. Just like there's a technical reason why you never learn about mean absolute deviation. You only learn about the square. Okay. So some of this mathematician try to create a matrix or the measurement that answer your narrative. Where's everybody? Is it big deviation or small deviation? So that's human language, right? But how that translates into mathematical calculation, that's up to mathematician. And you can imagine that if this was a long time ago, before they had computer, they had to do what's convenient for them. What's convenient for them is taking a square. Okay, so they don't take absolute value, for example. Okay, what else is more convenient for them? Well, taking an average is convenient for them. Taking the mode is not, because what they have to do is actually have to plot all the data points and then see where the top is. It's very hard. So you can imagine that this is kind of like mathematician doing things that's convenient for themselves. Okay, but the point is, after that's done, yeah, that's a bit cynical to think of it, but after that's done, this becomes the baseline. So now the most important measure of where the data are, you will never say mode. Nobody ever say, oh, I'll just take the mode. Even though in practice, sometimes you do that. Why am I spending a lot of time, even though this is so easy, it's not a technical answer? Because in your application, people, 90%, in fact, some of my team, my staff, data scientists, they would automatically, because of, they're well-trained, immediately go to the mean. Sometimes that's not what you want to do, right? Like that example of t-shirt. So remember that example t-shirt, okay? For the rest of your life, because that's exactly what I mean, okay? It makes sense to measure the mean, but no, for that case, mode is the most important, and nobody thought about it because mode is something that nobody ever talks about, okay? So beware. So now, do the same thing, except with respect to the deviation. You can also, again, then you have this max mean absolute deviation. So that would be 1.1, okay, 1.1.3 on page 98. So that's called measure of dispersion or deviation. Okay. Central tendency, where is it? In the middle. So where the middle, the center. So 1.1.2 measure of central tendency, 1.1.3 measure of dispersion. The other one is, well, remember skew rightness or leftness, right? So that's 1.1.4, page 100, measure of asymmetry. Asymmetry, okay? So even though you have the same mean, this could be because, sort of like same distance to the right, same distance to the left, or a lot of people small distance to the left, few people, large distance to the right. And you can do that like a seesaw, right? You can have a very heavy person sit next to the fulcrum and the very small guy, way out there. Okay, that's why you see when say sorry, you have to go. Yeah, that's okay. That's okay. I know. Got. Two of you, right? Okay. I'm gonna follow very strictly the book, so you don't have to worry about this. But do watch the video if you can. Okay. Good luck. Have fun. Now, this thing here, you can imagine if I did this and I do another one that's kind of like this, you can think of this as the tail, okay? So the more spread out relative to what you're usually seeing, you will call that heavy tailedness. Heavy / tail ed. Okay, it's not really a good word, but I can't, that's what they use, okay? Your tail is not that heavy, it's just far out. It's sort of like hanging outness, okay? So this is called heavy tailness. It's such not a nice word that people have to then invent, I think it's a Greek word called kurtosis. Okay, so now I don't have to justify what term I use. It's a hanging far outness. So I'm just going to call it kurtosis. Now, obviously, this has more kurtosis than this, right? Right? But if you think about it, this one also, look, man, has a bit of tail, right? What if some distribution has no tail? That would have like very little kurtosis, right? So now they have to say there is a baseline kurtosis, the normal kurtosis you can see. And this is by agreement. This is like Geneva Convention or something. They're saying that if you have this shape, okay, you calculate this formula that has square of the cube power, okay, but they have more term to it in the bottom. If they did this, they come up with this number and they calculate kurtosis for this is happened to be 3, exactly, precisely 3. Okay, so they call it, that's the normal kurtosis because that shape is so normal. Now I use the word normal, I'll tell you why it's normal later, but just trust me, okay? And you can see why this shape is also normal. You see it a lot. So now everybody is defined relative to this. So the term you usually see is not kurtosis. The term you usually see is what's called excess kurtosis. It's whatever kurtosis minus 3. Okay, because 3 is a baseline. So when you go to Wikipedia page, I don't want to sweep back and forth, but you can do that. If you go to any kind of distribution, you're going to get that. Okay, so now that is 1.1.5 measured of heavy tailness, 101. Okay, now I want you to flip back to measure of central tendency, but where are you? Yeah, central tendency, okay? Look at the table of a central moment on page 96. Okay. 96. The first column you will see is all 0 because I designed it that way. That data is centered around 0. Okay, you see that? The bottom table on page 96, right? Now, yeah. Look at the third line. The third line has the word normal, 0 and 1. Can you see that? You see that, right? Okay. And look at the last column. You see that number 3? That is the number 3 I'm talking about. Okay. So that distribution, the name is in itself called normal. Okay, I'm going to go to individually what each distribution means later. But right now, I just want to show you that's where I get the number 3. Okay, so you look at page 96, bottom table, third line, last column, you see the word number 3. Okay. So you might as well remember the 4 number 0103, 0103. Okay, this will be something very important. Okay, now. Okay. 1.2 is about scaling and normalization. I'll come back to it. Okay. So, what have we done so far? All we've done is to say, I'm going to summarize a whole bunch of number with a number. If I can do it with 2 number, I'll do it with 2 number. If I can do it with 3 number, I'll do it. I'll need 4 numbers. It's as much detail as I'm going to do. That's it, right? Okay, fine. However, now we're not in that world anymore, right? Right? Who cares about first, second, third moment? I can literally do histogram on any data on my Excel, right? In fact, I don't have to send the histogram. I can send the entire data set, you know, put it on cloud. My friend can download it and look at it himself, right? So no need to summarize. Okay? So no need to summarize. So why would you need to do any of this? I used to have to summarize because, you know, I only have Telegram. People are about, you know, 1.7 meter plus minus 10. So make the shirt or make the coffin or whatever of that size. But now I can literally put in copy this in an Excel and send it to the factory. The factory can make individual coffin fit everybody, right? Perfect. Why would I need to do any kind of statistics whatsoever? And this is why I want you to think. Why? Why? It's better. Why is it better though? Okay, that's economy, right? Economy. But there's another thing, which is, remember I told you, if you record what your mom likes to eat on Sunday morning, it's not data, it's information, because you are actually, you know what your mom likes to eat, have for Sunday morning. If I'm making 100 coffin for 100 people, knowing individual data is very important, right? In fact, if I could have it my way, I would not summarize at all. I would send all 100 numbers. My factory will make t-shirt to the exact size or the coffin to the exact size. It would be a perfect fit, right? No waste of wood for coffin, no waste of material cloth for t-shirt. The reason I'm doing this summarization even today is because I'm not interested in 100. That 100 is only a sample of 1,000,000, right? So that's why we have to extract the summary, not because I can't carry 100 numbers, okay? Because the 100 numbers is not what I care about. This is only my sample. I care about potential millions of people who can buy my t-shirt or coffin or whatever. So that's the essence of data, right? That's why even though I can take the whole 100 heights and shift it to my factory, that's not what I'm going to do. I'm going to send a model of the height of the people so that I can do my production planning for the next 100,000 guys, right? So that's a different. You, I really don't care. Once I take your measurement, you don't even have to buy clothes from me because you already done your job. I'm trying to sell shirt or coffin or whatever, or hat or bicycle to people like you. You are just a representation. So as far as I'm concerned, your value is the data. And that's why people of the modern generation get so many things for free, because they are taking data off of you. Does that make sense? Right? So if I turn on this air conditioner and I bring everybody a glass of ice cold water, right? And I don't charge you any money, okay? How am I making money off of you? Well, because maybe underneath the chair, there's a scale that measure how heavy you are, okay? So while you're sitting, I'm measuring how heavy you are. Or while you're moving, I'm tracking your movement. Right? While you're sitting, I'm taking a sample of the color of shirt. Right? So don't be surprised why you get so many things for free in life, guys. Because they want to buy your presence. Everything on the internet is free. The game is free. The Facebook is free. The TikTok is free. Everything is free because they want your presence. Once you have the presence, they can take the measurement off of you, and that's your value. Okay, that's your value, because then they'll say, okay, I can see that this shade of green is very good. Okay, so even though you already bought your greens, there are millions more who haven't bought that green. Okay, I'm gonna make green shirts, right? So this is where they say it's a little bit like they fatten you up. Sometimes it's a little bit cruel to say that, but sometimes they say, when they give you free stuff, it's like giving free grass to cows, because when the cows get fat, then they can make money off of the cow, right? But the grass is free. Nobody charges money to the cow or the pigs or the chicken. They eat for free, guys, right? But they derive value from it. So that's why you get all this free stuff, okay? So again, the summarization would have made sense back then, as a summary of the data, because you can't measure, you can't send 100 number. Now you can send millions of numbers. Why don't you do that? Because you really don't care about that initial 100. Okay, you want to extract feature. It happens to be, in this case, the feature is height. Okay, so that's kind of simplistic, right? So that's the idea, guys. So let me say that again. So data, not information. Okay, if you have 100 height and you're measuring exact fit for 100 customer, that's already information, guy. That's already making money off of you, right? No, I'm not. I'm not making money off you. I'm taking 100 of you. The only thing I care is to extract the distribution, because I know that the next 100, the next 1,000, the next million will have similar height to you. You are the sample that represent the numerical reality that I really care for, the big game, okay? The big game. So with that in mind, you can think of two reality, okay? Let's say that, well, let's use height. Let's use height. Height's easy, okay? Height's a very easy thing to do. Okay, height's very easy. I take 30 of you, okay? Let's say this is the real population, okay? Now, I'm gonna use, like, let's say I'm God or something. I know what everybody's height is. So this is everybody's height. Now, I'm gonna draw this shape often. I will justify later why this shape is the one that I draw all the time. And I will call this shape normal shape. And you will call this shape normal shape. And you will see this all the time. There's good mathematical reason why this is the case. But tell you, it makes sense. Anytime you have some kind of things where you can say, roughly speaking, it's symmetric. Okay, symmetric, not skew, not crazy, reach out. Everything that's center here is around here. That's kind of like a normal shape. So let's agree with that, right? So let's agree that this is the normal shape I see. And this is actually the height of the population. Okay, the height of a population. The height of the population will have its true mean. Okay, let's do this. Let's say the entire population of the Earth consists of 6 billion people. I take 6 billion people and now in reality, this is not enough. Why? Because when I'm trying to make a population estimation, I'm talking about people who haven't been born yet, right? But let's say this is a finite population. That's it. That's it. This is everybody's going to die after this and no more. Okay. So finite population of 6 billion. This 6 billion has an average height here. I'm just going to draw this shape. Okay. Now just make it so that 68% is between here and here. So I make 2 points. The point is where the middle is, and the distance such that around here covers 68% of the population. It's a kind of a nice number. Okay. It's born in 1968, so I picked 68, but actually that's not the reason why. But let's just do that. Let's do that, okay? So this is the real population. The process of taking you 30 at the time and take an average, right? 30 of you at a time and take an average. That is an estimate of what? It's an estimate of this number, right? Right? If I take the standard deviation of 30 of you, somehow it also gives information about this, right? But not exactly, because after all, the spread in 30 and the spread in 6 billion is not going to be the same number. Okay? But you can imagine that it's kind of like corresponding to one another. Okay? So for example, I can say something like, I take 30 of you, okay? And the standard deviation is 10 centimeter. Okay? The population standard deviation is not going to be 10 centimeter, right? But let's say I take your weight as well. And the standard deviation of your weight is 2 kilograms. The population is not going to have standard deviation in weight of 2 kilograms, but it will be another number. But you can see that there's kind of proportionality, right? So if you have bigger standard deviation in the height than the weight, the population will also do that as well. It'll be a bigger number, but it will be, you know, bigger and bigger, smaller and smaller, right? So it's kind of estimate. So the idea here, I'm going to write this as true population mu. This is number mu. And this, I'm going to call sigma. Okay, call sigma. The idea is that when I take 30 of you, X bar and S, this thing is going to give me an idea of that. Okay, it's going to give me an idea of that. It's going to give an estimate of that. Okay, in fact, X bar is mu. X bar will be the estimate for mu. So the word is, by the way, mu here, nobody knows but God, right? Only God can take 6 billion people, take their height, take an average, take standard deviation. However, the way I write it is like this. Okay? I want to know this. I use the estimate. I use the estimate. Okay. And I say something like, I don't know this. The estimate then will be this, or some with a little bit of adjustment. Don't worry about it. Okay. But roughly speaking, conceptually, okay? So that makes sense, right? I want to know how tall people are on Earth. I take an average of how tall people are in a sample of 30. I want to know how deviate people are on Earth. I look at the deviation in my sample, okay? So that's sampling, okay? So there is such thing as true distribution. True distribution is called population distribution. Okay? That population you will never know. Then there's a sampling that has its own distribution. But this you will get real sample from. Okay? Now this is a little bit, to be honest, this is a very difficult concept to explain. A population is basically 6 billion people, 6 billion people. Sampling distribution is not the 30 people in front of you. It's theoretical random 30 from population of 6 billion. Does that make sense? Right? Okay, let me say that again. So the total population has a distribution. So if you take the entire population, maybe including the unborn, and do the histogram, right? And you fit this curve, you will get what's called population distribution, the genuine distribution. How many people this tall, this tall, this tall? The sampling distribution is similar kind of distribution that you would get, okay, by taking a sample 30 at a time. So maybe it would look like this. Now, okay, so the difference between a sample and population is very important. I told you we're skipping the scaling, right? We'll come back to that. Okay, so now we go to probability theory proper. Okay, so I've given you the foundation, right? And I made the case that somehow you're going to get this shape. Okay, I will tell you that you don't always get that shape. But there are situations where that shape is not only the usual, it's the only shape. So now we have to talk about the distribution themselves. And this is where we start with probability. Okay. So once again, the whole thing is data analytics. You analyze data so you can draw a conclusion about population, right? In a more traditional confine of probability statistics, that data sample, they call it sample. They tend to, in your statistic class, they will consider everything as data, but the thing that you take and then you record, they would give it a name called sample. Okay, so it's a sample data. Okay, but data is more like a generic term. Anything you write down is a data. Okay, but if you're gonna take that, make conclusion about it, about the population, that thing is given a special name of sample. Okay. So it's a little bit more fancy. Okay, so the sample has a very intimate relationship with the population. But the whole thing, anything you write down is called data. Okay, the whole world of data. Okay, that makes sense. Okay, so now go to probability model. So this is where you throw away the concept of data. Throw away. Data is something you collect from reality, right? Something you collect from reality, and then that gives you an idea about the bigger reality. Throw that away. Throw that away. Take out your coin. When you toss a coin, before you toss a coin, do you have any data? No. So data is not real, guys. So forget about this thing about data come first. No, data comes last. Okay, let's start the world over. Let's start the world over. The world has no human being. God created the first man. Boom, he's 1.7 meters. That's where the data comes from. So God has to have a probability of making a human that's 1.7 meter. Before this, there's no 1.7. Data doesn't come first. Phenomenon come first. Okay. Now, of course, this coin toss and human being creation is an entirely different story, but you get the point, right? You can't think that data come first because what's the data on a coin toss? You haven't tossed the coin. There's no data. Until you toss the coin, there's only likelihood of a value. Okay. So before there's data, let's throw away. So section 1 is all about descriptive statistic. It's about describing the data, and it's going to be important because you're going to use this to infer about the bigger population distribution. Throw all that away. Start with section 2, probability theory. Now, probability theory is actually, well, you can think of it this way. Mathematics. Yeah. If I say data science is about asking where the values are and how is one related to the other, mathematics is about where the value can be and how variable can relate to one another. When I say where the variable can be, if the variable is a real number, it can be anywhere. If the variable is an integer, it can only take on integer value. If it's negative integer, it cannot be +7. If it's ratio, a rational number, it cannot be pi. You know that, right? Okay, pi cannot be expressed as a ratio of integer. Okay, so mathematics is about where can number be, okay, and how can you construct relationship between one number and the next. So it's not about finding relation between x and y. It's about can you construct y from x, and how do you do that? Function. Okay, so mathematics is all about variable and function. Fine, good, very nice. Except I just lied to you. Pen. Okay, watch this. This is very important. This is my x. Okay, x can be anywhere. Let's say a real number, right? If x can be integer, I'm going to put down a little point where it can be, right? So x can be anywhere. Where can x be? X can be anywhere. Okay, how can I make y out of x? I make it by function. Correct? Now, why do you say this is a function? Come on, think. Because it gives a unique value of y for any value of x. Okay? So obviously, this is not a function, right? Now, if I were to draw something like this, is it a function? Who says yes? Is that a function? Is that a function? No. Well, it is a special kind of function, but normally it's not a function of x. Why? Why is that? Because, yeah, I give you one x and you don't make up your mind, right? So y is a unique assignment of value to x. Okay, 2x can share the same value of y, But one X cannot generate two Ys. Cannot, right? Cannot, right? So that's mathematics. Okay? Except there's another kind of mathematics. And that mathematics has randomness in it. It's like saying, I give you X and the function will give you one Y one day and another Y on another day. That's not function, right? So mathematics almost has two worlds. There's a world where we call it deterministic world. Deterministic world. By the way, I'll give you this technical term. You just memorize it. This world is called deterministic world. Everything is determined. Y is a function of X. Deterministic world. Okay? The other world is called stochastic. Stochastic is a fancy Greek word for random. That random world has, well, randomness to it. So if I throw a ball, okay? If I throw a ball at this velocity, at this height, right? You know calculus, right? If I throw at this angle, at this force, at this acceleration, initially, it's gonna feel the effect of gravity, right? And eventually it's gonna come down here, okay? If I did this again, I'm gonna land on the same place, right? Right? Exactly the same place, right? However, outside of mathematical classroom, I'm throwing a piece of rock. Can you repeat exact same spot? Never, right? Never, right? In theory, if you can replicate your throw exactly, you land exactly the same place. What changes? Let's assume that you are not you, but you are a robot. So you make exact same throw, but you still don't land the same place. What could happen? Let's say this robot is perfect. It's throwing the right angle, right force, absolutely no deviation in the throwing mechanics. Well, the ball itself may have variation in weight. Maybe there's a wind blow, there's all this and that, right? So you can imagine that in a deterministic world, if there are so many tiny little factors, then you can have some uncertainty, right? Yeah. Okay, so this is one world. One world is calculus. Calculus ball goes from here to here. You can do it a million times. It's going to land at exact same spot. That's a calculus world. Real world, you have perfect robot, but the ball's not perfect. The wind is not perfect. And in fact, the robot is not perfect. So it's going to land approximately here or here. What happened when you put in the input and you measure the output as a function? You no longer get this, but you get something like this, right? And that's exactly why you do regression analysis. There is randomness, okay? So now imagine, I'm just gonna study the mathematics of just the randomness. I really don't care about this calculus anymore, right? I'm just gonna do the calculus of, I'm just gonna look at the variation. That makes sense? Okay. So mathematics relate variable y as a function of variable x. In reality, in engineering, in warfare, in baseball, in anything, you have uncertainty. So you don't land the bullet at exactly the same place. That's called uncertainty. Now, if you are shooting cannon from a tank and 5 miles later, you land here, you shoot another one and it lands 5 yards away. That's pretty good, right? Because the main story is you got there in 5 miles, right? So the small story of 5 yards away, that's inconsequential because you explode, right? So the main story is the deterministic part, not the noisy part. Okay, forget all that. Section 2, probability, is about this thing. Except instead of studying how does the wind affect the bullet, or how does the angle affect the bullet, you just say something affects the bullet, and it makes it high, low, left, and right randomly. So one interpretation of randomness is basically the determinism that's too tiny and numerous to take account for. Okay, so there's a reason why the bullet lands here, but you can't trace it. It may be something to do with the imperfection in the bullet design. There's something about the wind. I don't know what it is. Okay, but the point is, can you model this? So there's another mathematic that has to do with this kind of function, but the function is not y as a function of x, but the location of x, which in itself is a function of randomness. So it is in a way, in mathematics, you're going to have to do some kind of function, but that function then, instead of drawing out exact relationship, that function is going to draw out uncertainty. And that's why you don't study this kind of function. No. You study this kind of function, P of x. So x, now I'm going to make, in this case, I'm going to make it very simple. X cannot take any value. Let's say can take 6 value. It can take 1, 2, 3, 4, 5, 6. And I'm going to give it something like this. Okay. Now, my question is P of x a function? Yes. It's not random. What's random is the x. X can be 1, 2, 3, 4, 5, or 6, but for whatever value it is, I give it the right probability. Now, in reality, that probability will be coming from your data. Let's not do that. Let's not do that. Let's go to the world before data. In fact, to make the world before data reasonable, I'm just going to go to a coin toss because it's something you can have in your head. A coin toss is just something that has 0 and 1 as a result. You don't know what result that is. In theory, God knows, because this is the angle you turn the coin, and this is the momentum, and this is the air pressure, this is the blah, 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 and you can calculate, let's say God's own supercomputer can calculate this coin's going to land head. And if I toss it this way, slightly different, God can calculate, God's computer can calculate, it's going to land tail. But human computer cannot calculate. So as far as computer is concerned, it's either head or tail with equal probability. That's it. That's all you know. So now the only thing you have to get right is the ratio between probability of head and probability of tail. If the coin is good, it's going to be 50-50. So imagine this is your mathematical problem now. Your problem is that you knew if the coin was perfect, it's going to have 50-50. Right? Okay. Step 1. If the coin is perfect, you can have 50-50. Okay? In which case, the function looks like this. Okay? 0 and 1, and this is the probability 0.5. Okay? That's your model. That's your model, right? If you trust it's a perfect coin. Now, I want you to consider two situations. Number one, this is a perfect coin. If you were to toss the coin with 50-50 probability, exactly, this is the coin that God gave you himself. Okay, no cheating, no cheating, perfect coin. But you toss, you do the tossing, not God does the tossing. If you do the tossing of this perfect coin 1,000 times, will you get exactly 500, 500? No. So a perfect coin is not going to give you exact 500, 500. Situation one. Situation two, the coin you are given is not perfect. You also toss this coin and it's also not landing 500, 500. Let's say the first coin gives you 490 to 510. The second coin also gives you 490 and 510. How are you going to tell which one is which? The perfect coin is not going to give you the perfect 50-50 split, right? In fact, it's even possible, by the way, it's not likely, it's possible that a crooked coin will land even better, like 499 to 501. It's going to look even better, right? So good people can look guilty and guilty people can look good, okay? Right? A true coin can look 490 to 510. A bad coin can land 499 and 501, right? That is the challenge of probability. Okay, and that becomes module 3, which is statistic. How do you get estimate from coin toss? But right now, I'm going to bring you back to section 2, which is probability theory. In this world, let's assume we're having direct conversation with God. So if he says 50-50, it is 50-50. And your job is to work out the consequence. So the game plan is like this, guy. The game plan is this. If you knew the perfect model, because you're having direct discussion with God, it tells you this coin is 50-50, this coin is 40-60, precisely. You work out the consequence of what happened when you play with perfect model. And then you go to the real world and you play with imperfect model, and then you try to estimate your way back to see what is the best model that represent what you see. Does that make sense? So imagine there's kind of like there's a God process that generates the coin toss in the world, right? Right? You work out the consequence. That's section 2. When you go to section 3, which will be after the break, you go to section 3, it's the other way around. Now you don't have conversation with God. Now you're looking at the result of coin toss. And you work backward. What kind of perfect coin? Would it be perfect 50-50 or perfect 40-60? What kind of coin really would that be? Okay, now you don't care about perfect or not perfect. You're just trying to estimate. Okay, as far as you're concerned, 50-50 or 40-60, it's just a number for you to estimate. You just want to get it right. Yeah, because nobody's claiming anything, right? They don't have to claim. Unless somebody's claiming it's 50-50, then you test. I don't think this is 50-50. So you can see why that in the second, after the break, you come back, you have two mindsets. You either try to estimate what the real probability is, or somebody claim what the probability is, and you look at the data and you say, no, I'm going to call you bluff. Okay? I'm going to call you bluff. Yeah, 490 and 510. Yeah, I can believe that it's a 50-50 coin. But if you get something like 300, 700, I'm going to call you bluff. That's called statistical testing. Okay? So the first thing is to build up complexity, because the coin toss is so simple. There's only very few situations in life that can match this coin. So we have to build up a catalog of probability distribution. In other words, if this is one function, you need about 20. 30. Okay. Now, I'm going to show you on Wikipedia page that mathematician over the last 300 years has come up with about, say, 100 such function. Because I have done data analytics for large chunk of my career, will tell you that you need no more than 10. In fact, most of you will get by with just 5 distribution in life. Yeah, because they're really powerful. Yeah, one of them is that shape. One of them is that shape. I'll tell you why it's so important. Okay, but there are other shapes. So that shape is like Robert De Niro of probability distribution. You see him everywhere. Okay, right? And then their probability distribution that's a little bit more obscure actor. Okay, so now, just like I said, mathematics is always about where can X be and how can you relate Y to X. And probability theory is then about where can X be and what could be their corresponding probability. So with that, I'm going to have 4 kind of where. Does that make sense? 4 kind of universe. 4 kind of universe. Okay. X, there's this kind of universe. X can be here, 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 here. Okay? I call that finite. Okay? For example, X is the number of dots on a dice. How many dots can you see? 1, 2, 3, 4, 5, 6. You can't see 2.5. Now, let's say I have a naughty niece and nephew, erases all the number, right? And paints a different number on it. So instead of 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, my nephew put in -1, 1.5, 2, 2.5, and the other one put 2 as well, and then 7.2. Okay, my nephew is very naughty, right? My question is this still the same finiteness? It's still same finiteness. However, now two of them happen to be on the same block, right? So you used to have something like 1, 2, 3, 4, 5, 6 evenly spaced, even value, right? So perfect dice. 1, 6, 1, 6, 1, 6. So this is 1, 2, 3, 4, 5, 6, and everybody has 1/6 probability. Now my naughty nephew created another dice which looks like this. Can that be done? Yes. How tall is this probability? 1/6, 1/6, 2/6, 1/6, 1/6, right? Okay. Now, the point is not what the probability is or where the points lie. The point is it's finite. Okay. So this is case number 1. Okay. X, write this in your notebook or whatever. X belong to, say, X1, and this is a value. Okay. 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 So you can imagine that coin toss is one of those. Coin toss is one of those. Okay. So let's think of something random. Let's think of, well, let's go outside and time yourself 1 hour. and count how many buses, how many motorcycles come in front of you. Can you do that? Okay. So in your mind, before you go collect the data, that process itself is like coin toss, right? No data, it's just in your mind. First of all, what's the largest number you can see? Very tricky, right? Because it could be 0, that's small. 1, 2, could be 100. Yes. If it's 100, why can't I have another motorcycle? There's no law against it, right? So it is discrete value, right? But is it finite? Now, in your mind, it's not infinite. You can't have infinite number of motorcycles in front of you. However, in practical terms, can you guarantee that there'll be no more than exactly 500? No, because I can always say, what about 501? Okay, I'm going to bring a big notebook that has 1 million columns. So I can record 1 million motorcycle. Well, I can still say, well, you know, today is a really bad traffic day. There's actually 1,000,001 motorcycle. Is that possible? Not likely. Not likely, but is it possible? So in that case, this, okay, now just remember the word. Don't ask me why it's called that. The right-hand side is called support. It's like this. It's like, where can you be? Well, I can be on solid ground. Okay, so if you're not on solid ground, you get sucked into Middle Earth. Okay, so what is the support? Well, my support is this here. This is a good support. So where can X be? It's called support. Don't ask me why mathematicians call it that way. Okay, so the first one is called finite support because X can be in finite number of places. Okay, usually integer, but like we saw earlier, doesn't have to be integer, but it has to be discrete and it has to be finite, meaning you can say the first one, second one, third one, fourth one, fifth one, and eventually you stop. Okay, this is called finite set or finite support. Finite support. Okay, the second set, is it finite? Is it finite? No, because it never stops. But you can start counting. It's like one of those, I don't know, knickknacks or something. You know, you can start, you can't stop, that sort of thing. It's countable. You can say 1, 2, 3, 4, 5, but you can't stop. It's called countably infinite. Write that down. Countably infinite. Infinite, but you can count. Okay, you can say no car, no motorcycle, 1 motorcycle, 2 motorcycle, 3 motorcycle, 4 motorcycle, 5 motorcycle. You can't stop. So countably infinite or countable. Sometimes I just use the word countable. I think, in fact, in the book, I use the word countable. Okay. Now, I haven't gotten this part yet. Kind of flip the order a little bit. Now, the other case is kind of like opposite of the first of this. X can be anywhere between, let's say, 0 and 1. Can you count? So in other words, the randomness is alcohol concentration in your blood. That's a little bit unrealistic because, you know, after 6%, you probably die. You know, after 6%, you probably, let's say there's some kind of concentration, okay? That concentration goes from 0 to 100% or 0 to 1. So when you take a measurement, it's like a randomness, right? That randomness, can you count the output, the value? Can you say 0.1 and then 0.2? No, because it could be 0.11. So it's not countable. However, you know that it can't get beyond 100, right? So this is called bounded. Okay. Okay. Countably infinite. Okay. Now I'm going to give you two more. Then maybe we'll take a little break. What if I'm talking about the mass of an asteroid? Yeah, it can't be zero. It could be very close to zero. So let's call it zero, very tiny. It could be 1 kilogram, 2 kilogram. It could be a million kilogram. It could be larger than Earth if you think about it. Is it likely? No, not likely. So what's the range of value you can take on? It's uncountably infinite or unbounded. So you can go from 0 to, by the way, watch this, watch my hand. When I use infinity, because infinity is like the edge of the universe, you can't put a bound around it. I put a round bracket around it. Now this here is one situation. This situation is useful if you only want like one side. The number must be positive or negative. So what's this good for? Okay. Height is good for because you can't have negative height, right? But certainly you can have something like, right? This is called bounded. This is called semi-bounded. Okay. Where can that you see infinity and negative infinity? Well, most of the time you don't see, but anything you can't tell when I say infinite, it doesn't mean that you're going to get a high value. It just means you don't know when to stop, right? So even return, guys, just, you buy something, you buy a stock. It can have positive return. It can have a negative return. Can it give you 1,000,000% return? No, not likely. But the point is you can't stop. You can't say precisely, when I buy this stock, it cannot give me more than 3.0% because it could give you 3.01%. It cannot lose you more than 4%. Well, maybe it lose you 4.5%. Right? Right? So, in other words, well, it can lose so many percent so that it becomes worthless. Okay. So stock, for example, has positive return, has negative return. It's a continuous value. You don't know the absolute maximum. You don't know the absolute minimum. It's not going to be big. I know that. Okay. But mathematically, it's not possible to put a bound. Yeah. So the point is not, is it possible for the number to be that big? No, 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 no. It's about whether or not you can put a hard bound on it mathematically. You can't. So that's called unbounded. So you have finite, countable or countably infinite, bounded, semi-bounded, unbounded. Those are 5 places your random number can be, your random outcome. Now, again, the random outcome is usually something that has a meaning to you, like head and tail, right? Happiness or sadness. You ask the girl out and she said yes, no. You say, oh, you marriage proposal, yes, no. That has very important meaning, but mathematically we have to work with number, right? So become 0, 1 or 0, 1, 2, 3. All these are number. So obviously I'm going to ask you before we take a break, what kind of number scale are we dealing with? Look. So obviously these two are discrete. So this will be useful for nominal and ordinal scale, right? These two are continuous. Okay, sometime with zero, sometime without zero. So you're going to use those for what kind of scale? Interval and ratio scale. So you're going to see there's a very nice mapping, right? So this here I use when x belong to, so finite and countably infinite, those will be used for when x is a ordinal or nominal scale variable. Whereas the bounded, semi-bounded, unbounded support is used when the value of x come from interval or ratio scale. Okay, that goes back to class one. So let's take a 5-minute break.